So lab this week is the Project 4 primer. I just want to, so the grader in Autolab is live for Project 4 for enemy AI. If you had lab yesterday morning, just a lapse in my judgment and a crazy schedule, I didn't have the grader up at that point. So if you had lab yesterday morning, make sure you're submitting to Autolab, whatever you had at the end of lab, make sure you get that submission in, just so there's a record of what you've done in that lab. Move this mic. And today we want to talk about binary search trees. Before we get into that, I want to talk about trees a bit in relation to the homework. I'll spend a little time talking about the homework code for enemy AI. Oh, I gotta get the Discord open too. What's up, Dragos? What's up, Cole? So for the lecture task for this is the first trees lecture task. It's the only trees lecture task. The only other time trees show up is AO2, which is a bit of a beast. AO2 is a little tough. But for lecture task 4, this is where everybody is going to be using trees. And we have this make decision method, which is going to take a tree of decision tree values, which are going to decide how the enemy is going to behave. So each node is going to have a decision to make, whether that node controls what the AI is going to do, or if the action that the AI is going to take is in the left subtree or in the right subtree for the action of that player. So in this way, this is how the AI is going to decide what it's going to do. How is the AI going to make a decision? It's going to go into this decision tree, go into your LT4 method, and decide what to do by either going left, right, through the nodes, through the tree, or executing whatever action is at that node. I want to talk about, that might be tough to understand just from the lecture task text and the documentation. So I want to go into the code a little bit and explain exactly how that's going to work. Because there are a lot of moving pieces in the handout code, and I want to clear up some of that and just show you how trees are used in this project, in the homework itself. So let's talk about that. So make decision is going to return an AI action. So let's start with defining what an AI action even is, which is going to be in the message types file down here. So AI action is an abstract class which is extended by multiple case classes which are going to be used as messages in the actor system that control what a player is going to do. So if we send an AI action to the game actor, it's going to take that action and then move that AI character, do whatever that AI is trying to do. AI can do 4 different things: either move in a specific direction, stop moving, fire in the current direction that they're facing. This one is only used for human players that have an orientation of which way they're facing, and fire with direction, which is used by AI, which is going to tell that AI, say this AI is firing in this direction specified by the X and Y, so the AI can aim at a particular player. So move, stop, and fire are the 3 things that if we return one of those actions, that AI is going to take that action on that frame of the game. So the default value, I'm just returning move player with this player's ID and then moving in a random direction. Just math.random minus 0.5, that's going to give me a value from negative 0.5 to 0.5. And when you boot up the game, this is why the AI just wiggle around. They're literally every frame just deciding, or every AI update rather, which happens 10 times per second, which is different than the frames. I believe this is running at 30 FPS. Every AI update, they're just going to pick a random direction and then move in that direction for a 1/10 of a second. Not very interesting AI, of course. Once you get to LT4, this is where we're actually going to be making informed decisions based on this decision tree that we're given, which is a binary tree node, just like we've seen in class, which is provided in the homework code. So please use the one in the homework code. Literally what we've seen in class. a reference to the right node, a reference to the left node, and the value at that node. So we get this decision tree, and this is a decision tree of decision tree value, which is another handout class. This decision tree value is another abstract class. You can see where now that we know inheritance and polymorphism, we use this stuff all the time in programming. Any OOP program is going to use this stuff all the time. So there's an abstract class which has two methods, check and action. Check is going to return a negative number. It returns an int. That int will be negative if we should move left in this decision tree. So make a recursive call on the left node, or this one you could actually do iteratively. Move to the left node and then check that node, see what its decision is. If it's positive, go to the right. Check the right child, go to that reference, go to that node, and keep applying this logic. And if it's exactly 0, that means this node itself contains the action that you should be taking by this AI character for this update. If check returns 0, that means this node's action is going to be the action that should be taken, which is going to be of type AI action. And the game will know what to do with that and then move, stop, or have that player fire, have that AI character fire, depending on what the actual action is. So your goal for LT4 is to take this decision tree, call check, whether it's positive, negative, or 0, decide what to do with that value. And if it's 0, return that node's action from this method. This method returns an AI action. So if this node returns a check of 0, return its action. It's whatever it returns from its action method. Once you have LT4 written, so let me first jump over here. The AI actor class, which again is part of the handout code, all this I'm showing is the handout code, is going to make a decision based on that decision, this decision tree, which is the AO2 code. But the AO2 code has a default implementation in it. So we're going to call the decision tree for the AI player and then make a decision based on that tree that was given. And this is going to send that action to the game actor. Then the game actor is going to do whatever that action is. It's going to execute that action. The default, this is AO2, is to rewrite this method with more complex AI behavior. But the default AI behavior is going to, and you can see why this is an application objective. I wanted you to build the decision tree for LT4, and it's a bit much. So it's AO2 instead. So we're going to build that decision tree based on actions that the player can take, and then we're going to make one decision, and that decision is going to be a random coin flip and say if 10% of the time, if our random coin flip, our random roll of the dice is below 0.1, so a 10% chance, we're going to fire, else we're going to move towards the closest player. So hunt closest player is going to find the closest player using your code from the earlier LTs, find the path to that player. It will not avoid walls at this point because you haven't coded that yet, and then find the direction to move along that path. So calling all of your code from the previous objectives to be able to figure out how to move towards the closest player. Firing is just straight up fire, just fire in the direction that this AI is facing. And then we're going to have a decision node that will return -1 or +1 with children fire and hunt closest player to decide which direction to go in this tree. So we have a root node, which is going to flip a coin, effectively, not a fair coin flip. 10% of the time, move to the node that has the fire action, and 90% of the time move to the node that just moves that player to the closest player, the closest target. To get more complex behavior, that's AO2. If you're taking on the challenge of AO2, you'll build out this tree and have more complex decisions that depend more on the game state and you can read AO2, but move towards the closest player, avoiding walls, of course, And then once they're within firing range, within a certain range, they're going to start firing. They'll stop and then fire at that player. So this is the default behavior, that once you get LT4 done, this behavior will, you should be able to fire up the GUI and actually see your AI working. So after LT4, fire up your game again, fire up the GUI, run around the game, and see how the AI behave. They should hunt you down in a really dumb way. They'll hit walls and just get stuck on walls. And they will fire every once in a while, roughly once per second on average. So that decision tree will end up right here, because we're calling that decision tree in the method call of makeDecision. So makeDecision, that's going to get that decision tree from AO2 and then navigate the tree. For each node that I created here, 2 of these were action nodes, where action node just always returns 0 from the check. So if it's an action node, we're always going to return 0 and say this is an action that you should take. And if it's a decision node, we're going to call a function that we're given and decide how to move based on that function, based on the output of that function, which takes the game state. And then decision node should never actually take action, but we need some implementation there or else things just break. So if we ever get there, should never be called. But if you ever get a stop message for AI 0, that's a good debugging hint that something broke, something's bad along the way. Any questions on that? Is anyone even ready to think about this yet? I think most of the class is still on genetic algorithm. Unfortunately, it's only 2 days away. You guys got me nervous on that one. But a lot of the class is still working on genetic algorithm. Anybody have genetic algorithm questions, by the way? Is there anything a lot of you are stuck on? Yeah. If that YouTube ID is not in the map at all. So if it's not found in the map, so in your map you'll have a get or else, and the else will be 3. Would be the easiest way to handle that one. Anything else? Especially if there's something like a lot of people are stuck on, if I can drop a hint. Yes. Yeah. In LT4, I want to know that question if you remember. LT4 is, I said this before, but the biggest challenge of that assignment. If you're stuck on LT4, one of my recommendations is skip ahead to LT5 and 6. Get those ones done. Hopefully those ones act as confidence boosters. Hopefully you don't run into a snag on one of those. And then come back to LT4. You'll have more motivation to finish LT4 when it's your last lecture task. It's a lot easier to get that motivation to finish it off. When you have 2 lecture tasks ahead of you, it can just be kind of soul crushing. But LT4 is the bulk of the difficulty. That's the hardest lecture task. The hardest lecture task to complete. Yes. Sorry, what was that? Can you speak up a little bit? Testing for LT4. So a few things. What I like to do for testing LT4 is take that songs file that's in the repo and cut it down by a lot. Cut it down to like 10 lines or less, and then use that as one of your test cases. And since testing isn't required, you could throw it in a main method. Ideally, you'll have full testing, an actual test suite, but definitely cut down that file to like 10 or fewer lines. For your first test case, you can have like 3 lines in that file. Then it's a lot easier to run the debugger and figure out what's going on. And once you get that, a small file like that, then make another file with the same song rated multiple times, and then see how your code's handling that. If you can handle that for like 3 or 4 lines, you can probably handle it for thousands of lines. But if you're testing with the entire file, it's going to be, it's just hard to debug when you're clicking through for so many lines or hundreds of lines, it just gets tough to debug. So that's my first bit of advice is use a small file for testing. So that's a lot easier to check if you have every value there. If you're using the entire file, how do you even check that? It's a daunting task to test that. Is that what you were? Does that help, or was there something else you were referring to? Okay. And with this, I dropped this hint very subtly a few times. Maybe I should drop it not so subtly, but a map is very helpful for this lecture test for LT4. Use a map. If you're struggling, use a map. If you have a map that maps YouTube ID to song objects, that's backwards for you, to YouTube ID to song objects, it's a lot easier to, one, check for duplicates, and two, replace the old song with the new one with the new rating added. You just check, map.contains YouTube ID. If it does, get that song from the map, call add rating, and then put the new song back in the map. So much easier. If you're trying to do that in a list, and you're trying to remove an element from the middle of a list in Scala, it's a tough task. You can do it. You can use a filter and say filter YouTube ID not equal to the one I'm looking for. You can do it that way, but it's kind of painful and it's kind of asking for bugs. If you use a map, it makes the code a lot simpler to read and write. So I've dropped this hint subtly a lot of times too. The recursive method that you write, you get to choose the parameters and the return value. So maybe that return value is a map. Maybe that makes things a bit simpler to work on. And then when you get that map back, which maps YouTube IDs to songs, then in your original call, the method that takes a file name, then do just a little bit more processing to take the values in that map, convert it to a list, which is just map.values.toList, and then return that. So, and this is one of the tricks with recursion, is you don't have to deal with the data structures that you need in the end. In the end, you need a list of songs, but you don't have to work with your data in that format. You can work with your data in any format you want, any format that you find useful, which in this case, I would say a map of string to song. You can work with that data structure in your recursion, and then when you're done with the recursion, then just do a little bit of code to map what you have to what you need, which is a map of string to song to a list of song. So keep an open mind when you're writing your parameter list and your return value for your recursion. Use whatever values make your life easiest. And then when that returns to your top level call, worry about how to convert that to what you need in the end. But work with whatever types make the job easiest for you. Yeah, I don't want to read that, Cole. Anything else? I think that was a pretty good hint for LT4. Anyone who's hearing this, anybody watching the video or in this room, should be getting LT4 with that, at least most of the way there, I think. Yes?
So LT4 use the map, right? It comes out not ordered, unordered. So how would you order it?
So it doesn't have to be ordered.
I know, I'm just saying if you wanted to.
If you want it to be ordered, you would put all the values in a list and then sort after you get them back. Yeah, so if you wanted them to. But for this, that's part of why testing isn't required, because you got to worry about sorting. What do you sort on? YouTube IDs is the answer, but it's not trivial to get those tests written. That and the file names, dealing with file I/O and stuff. But my code will take, as long as you have the right songs. But if you do want ordering, maps are not ordered. You can use, there are some classes that are ordered maps. I don't even recall what they're called in Scala. In Java, they're tree maps, tree maps. But I would take the values, put them in a list, and then sort based on whatever I want after that list, after I have it in a list. So yeah, the default map in Scala, there's no concept of ordering. Oh, yeah. Yeah. Yeah, that's a tough one. That's tough. Yeah, that would be the answer. Just work with a map and then convert it to a list, then sort by whatever you want to sort by. That's a rough one. Sorry. Genetic algorithm AO1. I would need a specific question if I'm talking about an application objective. Trey, if you got I'll wait a little bit. If you got a specific question. Because if I just start talking about AO1, I'm going to end up repeating what's in the homework document. And, I mean, you can just read that. But if you have a specific question, if you read what's in the homework document and you're still like, WTF, I can help you out there if you have a specific question. But otherwise, I just don't know what to talk about. Because I could spend the rest of the lecture talking about AO1. If you missed your lab primer, the standard answer is to go to office hours, especially if you go to office hours with one of your lab TAs. They can help you out with the test cases. For AO1, you keep getting stuck at a local minimum. Any way to help that out? Always add, so for each generation, you're generating random animals, you're using the cost function to figure out which ones are best, and then the best ones you're moving on to the next generation. Before you move on to the next generation, don't forget to add random animals into that next generation. So if you just keep taking the best performing animals, what's the term? Crossing them over and mutating each one of those, you're going to end up in that local minimum eventually. So what you want to do is also add in a whole bunch of random animals that go into the next generation, just completely brand new, fresh animals that have nothing to do with the top animals of that generation. And then if you're in a local minimum, eventually one of those random animals will get into one of the other minimum, ideally the global minimum. And then once you get one animal in there, then they can start spreading their genes and start taking over the population, the whole animal pool. And then you'll be in that other local minimum. So that's the way you can hop around different local minimum. You have to have those random animals in there. That's the whole purpose of those random animals. How would I create a random list of doubles that you can use yield or I'd say yield is the best way to do it. It's the way I like to do it. Yield, new list of math.random, however many genes you need. So take your number of genes, write a loop that goes until that number, generate your list, yield your list, and then yield a list of those lists. Where the inner one can be 0 until 0 to, I always get 2 and until mixed up. But 0 to number of genes dot math.random. So that'll be a data structure. You can call your functions on that. Call map with a function that's just going to generate random doubles. And then those lists have those in a yield to yield however many random lists of doubles you want. But math.random is your friend in there. Somewhere in all of our first order function stuff, put that math.random and get those random lists. Oh yeah, list.fill. I was trying to think, I'm like, I know there's a better way to do this. List.fill gives it to you. Can you change what math.random makes? Sure. So math.random will give you a random double from random-ish. It's all pseudo-random. A random double from 0 to 1.0, and I think the 1.0 is exclusive. I don't know. It's rare that actually matters, though. But it's going to give you a random value from 0 to 1. You can throw some math at that to get it to whatever you want. You saw earlier in this lecture, earlier when I was going through this code, I shifted that range because I wanted a random value from negative 0.5 to positive 0.5. So you can shift it like that. If you want a random int, say you want a random int from 0 to 4, multiply, take math.random times 4. I'd be a little careful here. Times 4. If you want a random value from 0 to 4, you would multiply that by 5, right? That doesn't sound right. What's that? Yeah, 5 and then, why? It's sounding wrong as I'm saying it out loud. Just want to make sure I don't say anything wrong. But yeah, multiply by 5. That's going to give you a random value from 0 to 5, which 5.0, I believe it is not even possible, but if it is, it's going to be extremely rare. I believe the endpoint is excluded. And then you take the floor of that. You can either just dot to int or math.floor, whatever you can do to just drop the decimal portion and turn it into an int. So you can get creative with the ways you use math.random. It seems restrictive. It just gives you a value from 0 to 1. But you can shift the range like I do here. You can multiply the range to grow and shrink it. If I want a random value from negative 10 to 10, I'm going to take this. And times 10 it. If I want that as an int, two double, it's already a double. I'm just going to 2 int it, and that effectively takes the floor. So you can do a lot if you get creative with how you use math.random. You can do a lot of fun stuff with it. Yes? What was that? I did say negative 10 to 10. I did mean, yeah, you're right. So if I wanted negative 10 to 10, I'd have to times this by 20. You're right. Absolutely. So you can get creative with the ways way you work that. So if you want random doubles, you want your initial genes to not be 0 to 1. You want them to be 0 to 100. Multiply that by 100. Just take the random value you get and turn it into whatever you want. If you recall, the range is exclusive of 1. I was pretty sure of that. I just didn't want to say it too strongly because I wasn't 100%. Okay. Anything else on either of the homeworks that are out right now? So about BSTs. So binary search tree, I'll use the abbreviation BST or just say binary search tree. This is going to be a tree of not necessarily ints, but my examples will be ints with the less than comparator. And this tree has the property that for every node, any node in its left subtree, the value of those nodes are less than the value at that node. So like 5 at this node, every value in the left subtree is less than 5. Every value in the right subtree is going to be greater than the value at that node, so greater than 5 over here. And this applies to every node. This node, everything to the left is less than 2, everything to the right is greater than 2, same thing over here. That's a binary search tree in a nutshell. That's it. That's what a binary search tree is. And duplicate values depend on whoever's writing the code. Whatever library you're using, whatever code however you're writing the code. The actual definition of a binary search tree, like so if somebody an employer asks you like during a job interview or something, they say, how do binary search trees handle duplicate values? There's no one answer to that. It's going to depend on the implementation, on the language you're using, on a lot of different things. So the actual concept of a binary search tree. Now in each language and each implementation of a binary search tree, that implementation is going to have to decide how to handle duplicates. Some just don't allow duplicates at all. Some handle break ties arbitrarily, so either always to the right or always to the left. In my implementation, the code you'll see, I break ties arbitrarily. I do allow duplicates, And I think I always put them to the right. I'm blanking out off the top of my head. It's in one of the slides later. We'll find out the definitive answer. But this is what a binary search tree is. Everything to the left is less than, everything to the right is greater than. Binary search tree. Okay, so how and why? That's what we want to answer the rest of the time. The structure is pretty easy for this one. But how and why? So how, we're going to create a binary search tree class. And again, this is in the repo, just like any other code I show in lecture. So this is in the repo, and we want to make a generic. The lecture slides will use ints and the less than comparator. But to be generic, we're going to take a type parameter and a comparator, so we can have binary search trees with all the flexibility of our ability to sort. So for our sorting algorithms, we just took a comparator and a type parameter. We can do the same thing here, take a comparator and a type parameter, and order anything with any ordering. That's all within our capabilities of doing. This class itself is going to have one state variable, which is going to store the root of the tree, the root node for the tree, and have two methods, only two methods that we have to explore. Insert, how do we get stuff into this tree? And find, if I want to look for a specific value, tell me which node contains that value. So if I'm looking for a value A, maybe I want to find the value 5 in this binary search tree, give me the node, or at least a node since I'm allowing duplicates, give me a node that contains the value 5, and if the value is not found, this method will end up returning null. Greater than or equal to 0 and less than 1. Confirmation, I love it. I couldn't read that from there. It wouldn't necessarily be exactly half if you do math.random less than 0.5, but it's close enough for any purposes we want. It's all fake random anyway, so technically all the randomness is in math.random is deterministic. So we could compute exactly what it's going to return. So based on that pseudo-randomness, it won't be exactly a coin flip, but it's going to be close enough for our purposes. Yeah, and how they do it, I think it's wild hash functions, I believe, with a seed. They seed a value and then throw into this wild hash function, which turns it into another value, which is random-ish, and then returns that value. It's really interesting stuff, but there is no true randomness in the computer. Everything's deterministic. There's no actual randomness in our computers. It's all pseudo-randomness. But anyway, that's a topic for another a different class. Take probably quantum computing would be the place to talk about randomness and for pseudo-randomness. So we have our binary search tree class, and if we want to use it, we're going to give it a comparator and a type parameter. Again, int and less than, just for the lecture examples. Call insert a whole bunch of times. Then we can call find and find the values that we're looking for. So that's sample usage. This code here is going to generate the tree that we saw on the previous slide, or a few slides ago, to generate this exact tree. We're going to insert 5 at the root, 2 to the left, 8 to the right, 4 to the left, right, etc., to build that tree. We haven't talked about how to insert yet. Don't worry, I'll talk about that. So if we want to find a value, we're going to start with find once we have a binary search tree and we want to look for a specific value. This find's a little simpler than insert. I want to use recursion. Now, this is a case where I want this method to be the one that people call. If you want to insert something into my binary search tree, just give me the value. I'm not going to ask any more information from you than the value itself. So this is the method that I want you to be able to call. But I want to use recursion here. And in my recursion, I would like 2 parameters: the value that's being inserted and the node that's currently the candidate node of where to insert this thing. The current node that I'm exploring as I'm navigating this tree, looking for a spot to, I'm thinking insert. Looking for this value, this is the node that I'm currently considering as containing this value. So I want my recursion to have those 2 things. Alternatively, I could make this a method of the node class, and then I could have the recursion based on node dot left or right dot find, and then make the recursion all up here. Could technically do that too, but this is a case where the way I have things set up, I want two parameters. So I have my public-facing method that people are going to call, and then I'm going to defer to my helper method, my recursion helper, which takes the parameters that I want. In this case, I didn't change my return value. Like for LT4 on genetic algorithm, you probably want to change that return value as well, then do some extra processing in your public-facing method. So if the node I'm considering is null, that's my base case, one of my base cases, and I'm going to say if it's null, I haven't found this value, it's not in this tree, so I'm going to just return null and say, better luck elsewhere, your value is not in this tree. Else, I'm going to take my comparator and say if A comes before the node that I'm currently considering, then I'm going to check my left subtree. So if A comes before, or thinking of our ints and less than, if A is less than this node's value, I know that if A exists in this tree, it cannot be in the right subtree of this node. It can't be there because of the definition of a binary search tree. So if A is less than this node's value, I know that if A is in the tree, it has to be to the left. So I'm going to call my find helper method. I'm still looking for A, and I'm going to move to this node's left child. I'm going to move left in the tree and continue my search over there. If A comes strictly after this node's value, I'm going to do the same thing, but I'm going to go to the right. I know that A cannot be in the left subtree based on the definition of a binary search tree where everything to the left is less than, everything to the right is greater than. So if A is greater than this node's value, I have to go look into the right. If this node is in the tree, it's going to be to the right of this node that I'm currently considering because the comparator told me so. If A is not less than the node's value and the node's value is not less than A, using our less than or just generic any comparator, then they must be equal compared to this, according to this comparator. So I'm going to return this node. This node contains the value I'm looking for, and I'm going to return it. So I can use this comparator, even though our comparators only tell us one thing. Does the first argument come strictly before the second argument? Well, if we reverse the arguments and it's returning false both times, they must be equal according to this comparator. So for less than, A is less than node.value is less than A. They must be equal. What other choice is there? They have to be equal. So at that point we know we found the node we're looking for, and we're returning it. So our base cases are we found the value we're looking for, or we've gotten to null, and we know that the value is not in this tree. Our recursive steps are either moving to the left or the right, so we're always getting closer to that base case of null. If we keep navigating down this tree, we must be approaching null values. Eventually, if we keep going left or right down a tree, we have to get a null value eventually, unless we have an infinitely sized tree, which hopefully we don't have. Which could be possible if you mess up the code. If you have like a node, say a node's left and right child are both the root of the tree and it loops back on itself, then you got some problems. Then you got some broken code. You're going to break a lot of things with that. And we'll actually address that when we talk about graphs. Graphs are trees that are allowed to do that effectively. So back to trees, though. We want to talk about graphs until next week. So to find, say we want to find the value 4 in this tree, we're going to consider the root node, and we're going to pull out our comparator, which is less than in this case. Is this value less than the value at this node? That's true, so we're going to go left. Is the value at this node less than 4, the value we're looking for? Or I just flipped the arguments around and said, is 4 greater than 2? Yes, so I'm going to go right. And then 4, is 4 less than 4? Is 4 less than 4? Both of those are going to be false, so I know that these values are equal 4 is 4, so I'm going to return this node. Found the values I'm looking for. So each time we made a decision, we said, is 4 less than 5? Once that's true, we can eliminate all of these nodes from our search space. Anything to the right of that node, all of those values are eliminated, and we can move on to the left. Once we make this decision, all of these values, it's only 1 here, are eliminated, and we move to the right. So imagine this search tree had 1 million elements. Each time we make a decision, if it's nice and balanced like this, we're going to eliminate half of the search space. At this point, it should be sounding a lot like binary search. We're eliminating half of the search space every time we make a decision, and we quickly get to the value that we're searching for. I'll pause a little bit here. Any questions on find? We got insert, and then we're looking pretty good for binary search trees. Cool. All right. So insert, just a little bit more logic, mostly just bookkeeping, but we're following the same idea. We're going to ask each node, is the value that I want to insert greater than or less than you or equal to? We're going to make decisions based on that. So again, my public-facing method, I just want people to say, insert this value, and they shouldn't have to worry about anything else. If you're calling a method on a data structure and you want to insert a value, the only thing you want to worry about is what value you have to insert. But for my recursion, I want to have a second parameter, which is the node that's currently under consideration. So I'm going to write a helper method and then just defer to my helper method, which would be private in the sense that nobody else should be calling this except this method here and the recursive calls. And I'm going to write that to add my parameter and set up the recursion the way I want it, with the parameter list I want to, with the return value I want. Return value is still just unit. That didn't change, but I could change that if I wanted to. If I wanted extra bookkeeping, extra values coming up the recursion that I can add to each time a recursive call returns. So I'm going to pull out my comparator and say, is the value at this node less than the value I'm inserting? If it is, then I'm going to consider the node to the right. If the right child is currently null, I've found a valid open space where I can insert this value. I'm going to create a new node. It has no children, and it has the value that I'm inserting. So I'm going to look to the right. If there's nothing there, I'm going to create a node and add this value right there. If the right node is not null, I'm going to move to that node through a recursive call. And I'm going to continue the recursion at that right child of this node. If this comparator returns false, then I know that A is either less than this node's value or they're equal. So I'm going to break ties by going to the left. My guess was right in the earlier slide. I got to reverse everything. Going to the left. So we're going to go to the left, and we're going to break ties arbitrarily by saying ties go to the left subtree. If the left is null, insert this value right there. If the left is not null, make a recursive call and move to that left child. Oh, yeah, I should mention this too. If the root of this tree is null, we have a brand new root. So when you insert that first value, don't do any recursion because you're going to get null pointer exceptions. If the root's null, this is the new root. Else, we're going to start at the root and start our recursion. Dragos, if they're equal, we're going to put that value to the left. We're going to go to the left subtree. So I'm breaking ties. Just the way I wrote this code, I'm going to break ties by putting ties to the left. But we won't, like your quizzes, interviews, homework, that's not going, lecture examples, it's not going to come up. I'm not going to throw an example where we have ties, just because, it's not part of binary search trees, the concept. It's only part of each specific implementation. So I don't want to test that, I don't really care. At some level, you should understand that that's a decision that's up to each implementation. But I'm not going to drill you on that one in this course. It's just not that important of a detail. What's important is understanding the structure and the use of a binary search tree. Not getting caught up on one little detail of it. But my implementation happens to break ties by putting ties to the left. Our other choices would be put them to the right. As long as we're consistent, it always has to make the same choice. Put them to the right or don't allow duplicates at all. If you try to insert a duplicate, just say, nope, we're not going to do it. Which is very common, and that's a very common answer, is just don't allow it. Like if you're, like, I forgot to refresh my memory, but I'm pretty sure a Scala map, somebody can call me out on this if I'm wrong, I'm pretty sure a Scala map is based on a binary tree like this. So if you try to insert multiple values, the tree just handles that by saying, no, that's not allowed. Somebody can call me out on that if it's wrong. I know Java trees are. I'm pretty sure Scala trees are as well. You want to see how you can call a genetic algorithm function with the modified population? That's one where you might want a helper method where you choose the parameters. Because the genetic algorithm doesn't really take population as one of its parameters. You're going to want a helper. Like I was just saying, like it's on screen right now. You'll want another method that takes all the information you need plus the list of the population for the next generation. And then your genetic algorithm method will just defer to the helper method you write with the parameters you want. So insert, say we want to insert 7 into this binary search tree. We're going to check the root node. We're going to say, is the root node less than the value we want to insert? It sure is, so we're going to move to the right. We're going to do a check here. Is 8 less than 7? No. So we're going to look to the left. The left is null, so we found the space where we can insert. We're going to create a new node and insert that to the left child of this node. Oh, we have 1 minute. Let me just finish these slides. If you have a binary search tree, fun fact, do an in-order traversal, got the values in sorted order. So based on the definition, everything to the left is less than. You're going to visit all those first. Then you're going to visit the node. Then you're going to visit everything that's greater than it. So by definition, an in-order traversal traverses a binary search tree in sorted order. So if you want to sort values, if you have a balanced binary search tree, which means each node's subtree has roughly the same number of nodes. If you have a balanced search tree, you're going to insert the nodes, insert every node. Each insert takes log n time. N nodes is going to take n log n time. And then your traversal is going to take n log n time as well. And you effectively sort it in n log n time. One big advantage of this is that you can add new elements and maintain sorted order. So like a list, if you add an element to a sorted list, you have to resort the whole thing, and it takes n log n time. If you have a tree, you add an element, it remains sorted, and you don't have to resort anything. You just log n time to insert. But our tree is not balanced. I was very careful in the order I inserted things, the order in which I inserted the elements. But if we inserted in sorted order, we're going to add -3, 2, okay, go to the right, 4, okay, go to the right, 5, go to the right, go to the right, go to the right. And we end up with a linked list-ish structure, and all of our find, our insert, are both going to be O of n. Because we effectively have a linked list, we're not taking advantage of splitting the tree in a balanced way. So this gives us really bad efficiency. The way we coded it here, everything's going to take O of n. So how do we insert and remove also elements in log n time while maintaining a balanced tree? That's a tough problem. I'm going to leave that to CSE 250. You're going to study self-balancing binary search trees which, oh, you'll have a good old time. It's quite the topic. But that's not a topic for 116. I'll leave it to 250. For today, we're just going to use our inefficient binary search tree and call it good. All right, see everyone Friday.